I don't have the.
Let's do the default temperature.
Say again?
Will you help us with the default temperature?
Yes. Okay. So here, I'll show you, yeah, let me show you this. Mr. Davis,
Yes,
who made the right call about Priokai?
I saw the look on your face, sir.
Just say me. Just say me. Just say me. Which one is you? Which one is you?
Right here. Right here.
No, I don't care. I'm moving it. You fucked up.
That my grade's a little lower than theirs, so
Okay, alright, so.
Can you like move your bag?
No? Get, alright, so let me say this. Mass transfer. It's like conduction heat transfer
Both massive.
with different coefficients. How about that?
How about that?
So now this is the and mass transfer part of the entire semester.
Next lecture, sir.
Woo! Mass transfer. It's all in chapter 11. It's a short chapter. You guys can actually like review it on your own. It's not going to be on the final. It's not going to be on the final.
Okay.
But you will encounter stuff like this through your careers. You're going to have mass transfer problems, but they're going to be so far and few between that you'll be okay. You'll be okay. All right, so
Alright, so we're ready.
let's see.
He helps us with the default temperature, so we can get it done.
All right, so this, here we're going to have T infinity, T infinity, P infinity. At this point, we're going to have full stagnation. At this point in our airstream, we're going to have adiabatic wall temperature. So all of our convection calculations should occur between the surface temperature and adiabatic wall temperature. Adiabatic wall temperature is our new T infinity. Well, out here, we're also going to have omega. All right, absolute humidity, right? Absolute humidity. And the absolute humidity is governed by our, in metric, 0.622 times our vapor pressure, P minus PV. So what we want to do, this is general. It's like, okay, well that's great. What are we going to do with this to find? What are we going to do with this to find absolute humidity? What I'm saying is that if we look at
Yeah, sure.
altitude and PV over Psat. Remember, Psat is PG. And like in thermal land, sometimes you call it Psat, sometimes you call it PG. It just depends on the book you're using. So what I want to say is that we're going to be up at 41,000 feet, and because, and you guys haven't gotten this lecture yet because that's this afternoon. Moisture really doesn't exist in the atmosphere in meaningful concentration above 36,000 feet. It just can't get there. Okay, so at 36,000 feet.
so about 36,000 feet, you really don't have to worry about foggy or ice.
Of the DMI mass notification system. This is only a test. No action is required. This concludes the test.
Probably not.
So, we're going to assume, so when I say to assume when I say to assume a saturated atmosphere, this is what we're going to assume, that PV over PSAT is going to be 100%.
Once you get
1.0, what's it?
Once you get 36,000 feet.
Yeah, yeah. So from sea level to 36,000 feet, it's all going to be saturated. This looks like a really abrupt change, but the saturation level is so low up at 36,000 feet that it's not a big difference in moisture between 100% relative humidity and 0. But if there's 0 relative humidity, you can't ice up, can you? So for the first part of your descent, you don't really have to worry about icing. But that creates a problem, because if you get lackadaisical because you're cruising around at 41,000 feet and you don't
It's
have
too
any
high.
problem with fogging, you
Too
think
high.
you're okay. But then you start doing this descent and you're bringing this really cold thermal lag down with you. And it catches a lot of pilots off guard.
So what do you mean by thermal lag?
So the thermal lag, this canopy, it's got rho CP, it's got some volume.
We don't have to worry about it.
Temperature is the T invert T.
There's no relative humidity. So.
Okay.
It's the transient portion. This is the
I'll see.
Row C. I'd have to think about my units on this, whether or not the V belongs in there or not, depending on how I'm analyzing. Oh, and can't forget that. So this is our thermal lag. You know, if it was steady state, this side of the equation is equal to 0. But that's only so during the descent, you're bringing down all of this chilled, cold thermal inertia with you. And that's what catches pilots off guard, because they think their system's functioning properly at altitude because they're not fogging. But the problem is there's no moisture up there. Moisture's so low, they probably wouldn't fog even if their system was completely inoperable. So they don't really get caught by it until they start descending. Well, if you fog up, okay, you can just kind of fly around at some altitude long enough until your windscreen heats back up and it clears up. You might be out of fuel, especially if you're flying fighter aircraft. Fighter aircraft do one thing superbly. All fighter aircraft do one thing superbly.
Waste gas.
They convert money to noise. Unfortunately, that money's keeping you in that money's keeping you up in the air. So once you run out of fuel, you know, so we had a fighter aircraft ice up. We had the canopy ice up, and he couldn't come in for a landing because he had no visuals, and he was running out of fuel. Fortunately, fighters can speed up the process by giving it more gas to heat up the temperature on the windscreen. So the question is, do you tell the pilot to advance the throttles and fly faster for more aerodynamic heating, or do you tell them to conserve as much fuel as possible and have, you know, how does that heat transfer coefficient, you know, what do you tell the pilot? You've got a pilot who's up in the air, and he's looking at the possibility of ejection. $140 million aircraft, and he's going to eject out of it because it iced up. There's no way to land it. You're now hearing Bitch and Betty over the radio saying fuel, and you've got an incredibly calm pilot asking, you know, what do I do?
So this might be stupid, it might not work, but you know how some cars have like frontal cameras that let you see like where you're going? What if you try to use like a high-tech camera for those airplanes?
Well,
Would that
on
work?
and yeah, you can do instrument landing, but this is a situation that shouldn't have been encountered. This was a design flaw. This was a design oversight. So yeah, so fortunately we got Paul Metz down on that one, but we had to really rush to re-understand the problem and reschedule the heating on the canopy, because it's a inch thick Lexan. It holds thermal inertia very well. So this is the thermal inertia. It's bringing, even though adiabatic wall temperature is going to be greater than T infinity. So if your dew point, like T dew point at altitudes less than 36,000, that T dew point is going to be equal to our T infinity. So like in theory, it's like, hey, we've got this layer of warm air going over our canopy. We can't ice up.
T infinity or TA wall?
Well, adiabatic wall. So adiabatic wall is hotter than T infinity. It's not as hot as stagnation, but it's hotter than T infinity. So I go, wait a minute, we're always, this air temperature here is always going to be above the dew point. So if this air temperature is always above the dew point, how can we ever frost? The reason it would frost up is because this is pre-cooled and it's going to have thermal lag. So even though this adiabatic wall temperature is above the dew point, the surface temperature, our surface temperature is, in some cases, not going to be above the dew point. So you want to evaluate relative humidity, which is going to be you want to evaluate the relative humidity at the wall and make sure that that remains less than 1.0. So you want to look at your wall temperature. So your wall temperature, right, PV, all right, all right, so.
But we need to look at this in terms of temperature, not pressure. So how we...
Yeah, exactly. So PV comes from our, if we're fully, all right, so remember, omega at saturation is going to be equal to, this pressure is our total moist air pressure. It's not the air pressure. This is P ambient, P infinity, So at saturation, our vapor pressure is going to be equal to the saturation pressure that's in the tables that I gave you. So our tables, we've got a T and we've got a P sat. Sometimes I call P sat PG because the different books call it different things. It's confusing, I know. So this PV comes from, this PV is actually our P sat. Our P sat evaluated at T infinity. This guy down here is going to be P sat evaluated at whatever our model tells us our surface temperature is. That's, yeah. So we've got our canopy here. We've got a, let's say it's a 5-node model.
So should we look at this in terms of pressure instead of temperature?
No, because we don't really care what. Okay, we do care what the pressure is, because this is our outside air pressure, and we're going to assume 100% relative humidity. So that means that P sat's going to be at saturation, so our vapor pressure is going to be the saturated airstream vapor pressure, and we want to evaluate it at the saturation temperature conditions at T wall. So we're going to have, I don't know, 32, 45, whatever our T wall is. And I don't know what this, so we want to use the interpolation function. So whatever our TW is, we want to feed that into our interpolation function to find our P sat to determine what our.
Okay.
Sure. When I was running mine, I've got it all the way to like finding the temperature of the wall, and then comparing that to like the temperature of the cabin before I even added the electrical heat from the like embedded part.
Yeah.
And it's keeping my like inside my window already like within the parameters. Is that like off?
That can't be right. If you're not
What's your
It starts at
initial
100.
What's that?
Starts at 100.
100 what?
I guess Fahrenheit. It's just what you gave us in the example.
Isn't like the initial.
That has nothing to do with this problem, though.
Yeah.
So that's.
Would it be a wrong assumption to say that we could just initially heat our canopy to that?
Well, not for the first step, it would be wrong. But what you want to do for. Yeah. So for your. Yeah, you're.
I mean, you might have to see my code to get what I'm saying.
Yeah. No, I know what you're saying. You're not steady state to start with.
Mhm.
If your canopy is if you have no Q dot and your initial canopy temperatures are 100 C or 100 F.
So you're saying I need to start my initial canopy at like 0?
Or you need to start it at whatever steady state is.
Because remember, like we're starting like at 41,000.
Should we find
for
this
a while,
steady
and
state
then we're
with a
going
Q
down.
though, or without?
So it'll like stay at that.
Find
I need
your,
to find a steady state at cruising
it's
at
two parts, so
41,000
you're going to do it.
Which I guess it doesn't matter
That's
because
why I
we're
said
at
like to start at
41,000
-3
feet,
seconds.
so it's not going to fog up
Still
anyway.
get to steady
so-
state.
Yeah, but you still need to know what you want to do. So you're not steady state to start with. That's a problem. So
that's
here's
what I
what you want to do. Here's what you want to do. You want to be at 41,000 feet. You want to start your model. This is in seconds. Start your model at minus 300 seconds. That seems weird. Why would you do that? Well, you're going to have, if this is temperature and this is time, you're going to have an initial guess for the T. So you got some, or maybe in your case, all right. So you said that your initial temperatures were 100 degrees C all the way across, right?
Fahrenheit, yeah.
Well, it's probably C.
If it was the
Did you-
Holman one, it was C, I guess.
Or if it's coming from the example I gave you, that's C.
Okay.
So
Talk about the Holman example, or the example was good.
The Holman example.
the Holman example should be C. So
Yeah, Celsius.
so I'm failing a color right now. So what you're going to do is,
Yeah, makes sense.
you got something really high. You got a starting condition up here. You got some T init up here, and both. So your inside temperature is going to hopefully come to something like this. Your outside temperature is going to go like this. And once these temperatures are no longer changing, the temperatures aren't going to be the same. There's going to be a temperature differential. The outside of the window is going to be colder than the inside, right? If you're 70 F on the inside, you're minus 40 F on the outside, okay? But you gotta run it for some time to figure out what your steady state conditions are. And this is so your temperatures are so hot. Yeah, your temperatures are already above your temperatures are above 212 F. So you're already like 40 degrees higher than the max allowable.
Okay.
So, see, you were, like at 20 minutes, you were just here. So that's why it looked like it was okay. You're, so you didn't have any heat, so your Q dot was 0, but your initial temperature was so high that you were never going to fog during the 20-minute descent because there's so much thermal lag. So you gotta get initial conditions.
Do you want us to show you the without heat gen, or
Yeah, I need to see a descent without heat generation. That's the baseline by which I'm judging your model to be accurate or inaccurate.
do you want us to show that in our report, or you just want to see that?
Yeah, that's got to be your baseline.
I mean, that's part one. I mean, like the first step, like just show.
Yeah, your first step is a baseline descent without heat generation.
Just
how
like
how do you
all
want
of
these turned in? Because 1500 Excel.
I don't want to see that. I want to see a graph.
Just a graph.
You want a graph of
Would
it?
you tell us like what kind of graphs is like, sir? Like which relationships?
Well, the important ones.
And also, sir, isn't it a safe assumption to say that your initial temperature be like similar to the adiabatic wall temperature?
For the exterior point, yeah, it's going to be close. It's going to be within 5 degrees.
Okay.
But you know, it's not going to be it's not going to be the same temperature all the way through the canopy. It's going to get warmer as you get
So how exactly do you find your initial gas?
closed form solution. This. Keep doing this until you get no change.
Take your code and make your convection coefficients constant, and make your inside and outside temperatures constant, and just run it for like 500 seconds.
Yeah, you need to.
Will our interpolation function go away if we add extra seconds? We're going to
in
redo
fact,
that.
It'll happily handle negative time.
Okay.
The easiest way to figure out what your initial conditions are is back up in negative time.
So we can drag. Can we drag that up?
No, you don't want to drag it
that's
up.
what I did. I went to negative
You don't
time.
want to drag it up. What the function does, because my descent profile is from 0 to 22 minutes, right?
Mm-hmm.
So if you have like minus 600 seconds, remember, make sure your units are right, because I'm talking seconds and minutes. You got to make sure these seconds are converted to minutes, or convert your table from minutes to seconds.
Okay.
Yeah, yeah. So if you're getting a really funny descent rate, you know, you probably have seconds and minutes switched around. So the lowest value we have is 0. The way my interpolation function works, if you give it minus 600, it's just going to hold my descent profile. My descent profile looks like this.
So you should do like, say, negative
41,000
600.
feet. My descent
Negative
profile looks
initial
like
gas. By the time we get to
looks
zero,
like
it
this.
should be stabilized, shouldn't it?
Mm.
Just don't take a stupid graph. Pick something that's kind of
Yeah.
41,000 feet at time 0, and this is like 22 minutes out here. So if you give the Excel model minus 10 minutes, what my function does is it says, okay, I am beyond my last available data, so I'm just going to hold my last known data point.
Mm-hmm.
There's a flag in there. You can do like a (1), and it will. There's an optional flag that'll let you extrapolate beyond your last known value. But if you turn that on and extrapolate, you're going to be descending from space.
Yeah.
Okay, so just leave it as the default. So it'll basically never land you. Like your speed will just keep on trucking at 0 altitude, 0.3 Mach. If your model runs beyond 22 minutes, it's just going to keep you flying at 0.3 Mach along the runway forever. But that's better than extrapolating. And if your time is negative, it's just going to hold you at your. If your time is negative, it's just modeling steady state cruise, and that will help you determine. So you got to take an initial guess. It's like, oh, this initial guess is too high. So then come back in and take an initial guess here with some temperature differential between the inside and outside of the windshield, and then that initial guess will come to steady state sooner because it's a better guess. This is not a good guess. This is a better guess. So it'll give you the right answer sooner.
So which of those curves is the inside and
So
outside
that's what you do,
again?
just graph and then just play the numbers.
So are we gonna have to convert all of your units from metric to?
I've lost faith in you guys being able to do that. So
Can we give?
I will have charts that do it in F, I will have charts that do it in C, I'll have charts that do it in K.
Yes, because I know like your K value, for instance, is like in BTUs. And we'd have to get them
My
like
K value? Not the K value.
the standard atmosphere.
What's that?
The standard atmosphere one.
No, I
There's
gave
two
you
tables.
stuff in metric too.
Yeah, there's two.
I gave you stuff in every unit system known to God.
It's called T drive.
Oh,
Yeah, there's a new one on T drive.
I think I used the wrong one.
Yeah. Probably.
Well, there's a new one in T drive. I erased the other stuff in Canvas because Canvas wouldn't let me update it. Canvas wouldn't let me change it. So
All,
use
all
your
last night was a waste.
That's
No.
how I feel, dude. It's been
no,
so
because
hard.
you're already if you're working in a consistent unit system, it should work out.
Sir, do you have answers for Kelvin, Celsius, or like whatever?
Yeah, I will.
Fahrenheit. Okay.
Yeah.
So. we can compare it with yours.
All right. So what you guys have to decide is whether or not you want to bug me with questions that you could answer on your own, and not ever get your tests back, or let me grade your tests, and then all right. So, no, there's only so many hours in the day. I got home at 3 o'clock in the morning. I was back up at 6, coming back into work. All right. So only so many hours a day. I got a 2-hour staff meeting after this, where I've got to be yelled at for 2 hours for not scheduling the final properly. So our final is scheduled during lab period, all right? But I had to, even though we're not required per official VMI policy, the internal department policy was to actually file a general permit, of an actual permit for that move date. So I didn't realize that, so I'm getting yelled at for pushing the final out from the normal class time to the lab time at the end of finals. So that's how I get to spend my next 2 hours. Not helping you guys, but getting beat over the head for that. So your function's going to happily go to negative time, and it'll just safely hold your last value. That's a good thing to do. So if you're ever beyond what you have data for, it'll make your model more stable. If your interpolation functions extrapolate and your model gets out of bounds, really wild things can happen, and your model will blow up.
Yeah.
So keeping it stable is really key. So that's why my function does that. Vapor pressure. Our vapor pressure only goes to 32F. That was my time. What's going on?
Yeah, how do we get that?
You were showing us the useful graphs we need to show you.
Yeah, plot out your saturation pressure.
How do you make the curve for it though? I saw that there's an e to the a, e to the b curve, but I don't know how to make
Oh, it's a curve fit function.
Curve fit function in Excel.
curve fit.
Yeah, curve fit function in Excel.
Going back to this time thing, is that going to give us, when we're at steady state, like a temperature that's just constant up there?
Eventually.
And then we're going to take that temperature, go over to like the Holman example and plug that in where the 100 degrees Celsius is?
Yeah.
And that's like our baseline.
That's your plug in that temperature distribution.
Do that.
Yeah.
You have to plot
Aren't they all going to be the same
and then
values?
Find the
No,
function.
no, it can't
It's
be.
a function like
The
this.
cabin's gonna be hotter
A,
than the
e to the b.
You got heat flux coming through your window, so the inside
It's like
temperature's
your,
gonna be
it's
hotter
like
than
your,
outside.
your temperature like of the outside wall, which is like this.
And the temperature of the inside.
You're going to have your
wall's
temperature
be hotter.
steady state, which is like across the top.
Well, it's going to be a diagonal.
Like your
I know
5
you're
nodes
gonna
that you
get
start
the
with on the
A
top.
and
What
the
are those?
integration.
Where do those
Yeah.
numbers come from? Because I think that's where my program's like messed up.
Well, it should be
your
in terms
temperature.
of t.
Right now,
so
my
you should
top
be
like
able
5
to
nodes
plug
are
it
like
into-
100, 100, 100, 100,
Because
100.
it'll be in
Yeah.
terms of t when it comes out,
Yeah,
right?
you're
So you
saying
have
it
t
looks like
somewhere in
this.
here.
Yeah.
It should
So
at
just
least
put
look
your,
like
And then
this.
you should be able to put that in and it spit
But
out
really-
the pressure.
Really, it should look like, your initial gas should really look like this. Okay? This is what your initial temperature distribution should look like.
For T wall, right, sir?
Oh, for each
Yeah.
node, it should go from -40 to negative
Okay.
10 degrees Celsius.
Yeah, because you got,
Mine was higher than that, and it's 70 degrees Fahrenheit inside.
So
So
mine
would
is
70
what?
degrees not keep it above negative temperatures?
no, because your convection coefficient's so low.
Yeah. I'll have to fix this.
So remember, this temperature here is a function of HA delta T. It's a big delta T. You know, you've got a 70 degree, you've got a 20, you got a 30 degree delta T, but your H is like 1. So your heat flux is, you don't have enough convection. That's why you don't have enough convection inside the cockpit to really
Yeah.
naturally keep it warm. That's why we typically blow hot air on the inside to give you a higher convection coefficient.
Right.
But blowing hot air on it is noisy, it dries out the pilot's eyes. It's just a disruptive thing to do. So that's why we put the resistive heating in the middle, the QDOT. So, you know, because this stuff, you know, for 12, 16-hour flights, that stuff beats you up over 12 to 16 hours. So you want to keep it more like an office environment. Right?
Sir, can you tell us again? We're starting to over here, but we sidetracked you. Can you tell us what graphs you'd like us to display, like what the relationships in the final
Yeah,
solution?
okay, so you want temperature. You want okay, so this is inside temperature. This is outside temperature. What's going to happen is that
You say inside on top or outside on bottom?
yeah, because the inside temperature's got to be
Higher, yeah.
it's got to be something hotter. So what's going to happen is your outside temperature is going to kind of go like this. So you're going to get a temperature inversion. T-wall out. T-wall inside. And you're going to have a you're going to have a your adiabatic wall temperature is going to kind of look like this. Your adiabatic wall temperature should start out colder than your outside temperature, right? Because, you know, you've got,
It should be pretty close though,
it's going to be
right?
close, but it's going to be a little bit colder. But once you descend, your surface temperature is probably going to be at some point in time colder than your adiabatic wall temperature because of your thermal lag.
Right.
If you just hung out at that altitude, these two things would essentially be equal to each other.
So I'm getting like, how to get you like your 1 in 5 for like the node temperatures. What my question is like, how do you solve for like the infinity, like the